To make an infection control decision, laboratories are using phenotypic tests, as we just discussed. You could also use a molecular test to look for a resistance mechanism. Or what I'm going to propose to you is that you could just look at the susceptibility profile and make a decision. And the reason I'm going to propose this is because it gives you the simplicity and speed. And simplicity is good in a laboratory, and I think for infection control, speed is a good thing as well. And so let's go through each of these options. So there's the phenotypic test option, and there's the ESBL test. Well, there are problems with the ESBL test. And the problem is when you have an isolate with multiple enzymes, for example, an AMP-C and an ESBL, you're going to get a false negative result using this ESBL test. So you would undercall the number of isolates that might be important for infection control. That's one of the reasons this test is no longer recommended for treatment decisions by CLSI, and it's another reason why I'm saying it's not the best test for infection control. There are phenotypic tests that have been proposed for detecting AMP-C type enzymes. There are ones that use different inhibitors. Cloxacillin has been used, boronic acid has been used. And these have never occurred in the CLSI documents. And there are a couple of reasons for that. One is sometimes these are patented tests, and that would not fit into a CLSI document, which is meant to be multiple source testing. And also, many of these tests have not undergone sufficient validation. And it's not that these validation studies haven't occurred, but usually they run into problems, and they run into the same problems as the ESBL test. When you have isolates with multiple enzymes, you get false negative results. And there are more and more isolates around that carry multiple extended spectrum beta lactamases. So these used to be very rare, but they're becoming much more common. So I think all of these phenotypic tests are going to run into problems because of this. Then there's the modified Hodge test that's used for detecting carbapenemase producers. And this is a test that our laboratory promoted. And I'll be the first to tell you that this test has problems. So one of the nice things about this test is it does detect all carbapenemases. I'll tell you about the spectrum of carbapenemases in a minute, but there are now there are KPCs, there are NDMs, there are IMPs, there are VIMs. These are all occurring in Enterobacteriaceae. They're all important. And the modified Hodge test is nice because it will turn positive for all these different carbapenemases. But it is a subjective endpoint. It's hard to read, and that's a big problem. Also, there's problems with specificity. If you go into a laboratory and you test your normal population of Enterobacteriaceae, it's a pretty specific test. We measure that specificity, and it's greater than 90%. But then we also looked at the problem isolates that were sent to the CDC, and for these isolates, the specificity fell to 64%. And that's low. So these are isolates that test non-susceptible to carbapenems, but we don't know the mechanism. Okay. And if you do the modified Hodge test on those, and then you do specific tests for carbapenemases, those are the isolates. And specifically, these are mostly Enterobacter species. You could use molecular tests, and there are actually good molecular tools that are coming to market. And here I highlighted the checkpoints assay. This is the microarray assay that can detect multiple extended spectrum beta lactamases. And this slide actually needs to be updated because now the newest version of this test will detect the new Delhi metallo beta lactamase, which has been a big news item recently. And it will detect KPCs as well as ESBLs and a whole lot of other things. So I think these tests are good. They're expensive. It's about $50 to run one of these tests on an isolate. What I would propose is that you could use susceptibility results to make infection control decisions. And I'll tell you some proposed definitions for identifying isolates. Now, these would be definitions used with the new breakpoints. So this is when you've implemented the new breakpoints, but you're no longer using the ESBL confirmatory test or the modified Hodge test for making treatment decisions. Well, I'll propose that for defining cephalosporin-resistant Enterobacteriaceae, you could use the definition of isolates that are resistant to either ceftazidime or ceftriaxone. Alternatively, the definition could be isolates that are resistant to ceftazidime or cefotaxime. And then for the carbapenem non-susceptible Enterobacteriaceae, I would propose that any Enterobacteriaceae that tests non-susceptible to a carbapenem should be identified for infection control. And the reason I propose that is because these isolates either have a carbapenemase or they have a plasma-mediated AMP-C that's combined with a porin loss, or it has a plasma-mediated ESBL combined with a porin loss. And all of those are isolates that you would want to identify for infection control. Any kind of plasma-mediated extended spectrum beta-lactamase, I think, would be an appropriate use of infection control resources. So these cephalosporin breakpoint definitions we wanted to test. And to test this, we applied these definitions to the isolates. It was a retrospective data source. These were the isolates that were tested to validate the ESBL confirmatory test for CLSI. And basically, this is the analysis we did. We asked whether resistant rates using these definitions would differ using different breakpoints. And the isolates were the isolates from the CLSI ESBL study. And this is the result of that analysis. So under old breakpoints, these are the old CLSI breakpoints using the ESBL confirmatory test. And then under new breakpoints, these would be implementation of the new breakpoints, but not using the ESBL confirmatory test. And if you apply the definition of identifying any isolate that is ceftazidime or ceftriaxone resistant as an infection control isolate, using the old breakpoints, 30.3% of the isolates would be identified, and using the new breakpoints, 31.7% of the isolates would be identified for infection control. And you see, if you go down using the other definitions, either MIC testing or dysdiffusion testing, the rates of resistance are almost identical. So I think you could just look at the susceptibility results, be able to identify isolates that are infection control concern. It would be simpler and faster.